Okay, good afternoon. I'd like to welcome everybody to our first installment of this exciting new series presented by Melissa Birch in Inner Health. My name is Jenny Wozdek, and I will be your tour guide over the coming months as we speak to a wide and impressive variety of scientists, philosophers, and homeopaths, exploring ideas that will help us more deeply understand how homeopathy works. We're extremely privileged to have as our debut speaker today Professor Rustum Roy, who will be sharing his innovative research on the structure of water. You've all had a chance to read Professor Roy's impressive biography and list of accomplishments, but I'd like to highlight a few in way of introduction. Professor Roy is speaking to us today from Penn State University, where he is the Evan Pugh Professor of the Solid State, Emeritus, and founding director of Materials Research Lab at Penn State, a world-class research facility. Over his illustrious career, Professor Roy has published over 1,000 scientific papers and is one of the most referenced researchers in materials worldwide. He's also been elected to the National Academies of Engineering and/or Science, not only in the United States, but also of Russia, Japan, Sweden, and India. He is an equally well-known and active participant in societal and religious thought and institutional reform. So welcome, Professor Roy.
Thank you very much, Jenny.
You're welcome. So feel free to start when you're ready.
All right. Let me start by saying everybody's got the picture that I'm a materials scientist. I'm a chemist by training, and I've been I helped start the field of interdisciplinary materials research. So that includes physicists, chemists, engineers, and so on. But my training is basically in chemistry. I'm a kind of a disciple of Linus Pauling. He was very close to us, and I was to him. And that background has been used in what we will be talking about today.
Great.
Let me tell you what I'm not talking about.
Okay.
We do nothing clinically about homeopathy. We do not establish that clinically it works or it doesn't work. I happen to think it does work, but nothing of what I will talk about today or our science is clinical or with healing outcomes, anything. So please note that this is all about the science of water.
Great. Thank you.
And so the difference in what you will hear today is probably quite new, because most people, if they get interested in the structure of liquid water, now water sometimes refers to H2O molecules and the stuff in the air and all that, so that's not what is involved in homeopathy, and it is totally irrelevant, but it is always cited. So we have put material science, that means condensed matter, that's the other word for materials, condensed matter, not a vapor, it's either a liquid or solid, that kind of science to work on looking at homeopathic remedies.
Right.
The bottom line that you will get from this talk is this work now demolishes the argument. I use the word demolish advisedly. It demolishes the argument which has been used for a couple of 100 years against Hahnemann and against the idea of homeopathy, because it says the original liquid, if it is so diluted beyond Avogadro's number and all those magic words, that means there's nothing left in there, so it can't possibly work. It is the implausibility argument which has been used to totally destroy the possibility of homeopathy. The thing is, try it and see. Look at the clinicals. That's the appropriate way to do it. But now we have demolished that argument from just regular physical sciences. And that work is now in a series of papers. The first one is the one that we will be giving you the data on today. There are 2 or 3 more. The latest one is just accepted this week in another materials journal, and it says its relevance to homeopathy. So let's start on this one. Here's a citation. It's in the, I don't see the citation, Materials Research Innovations is the journal, is December 2005. It's somewhere, but that's the paper that we'll be discussing, and stuff relevant to that.
Great.
Okay, so, well, the first one is quite obvious. Water is the single most...
You might want to tell them when you change slides so they can keep up.
Oh, this is the first slide. The top of the slide is water and health.
Great, thank you.
Okay, now, well, obviously, I don't think people appreciate that first bullet. Water is the single most important component. How important? It's what we look for on Mars. We spend, including our lab here, I was the first person to look at the lunar rocks. And I said, can you find any water? Well, everybody said, no water, no life, right? It's that fundamental. On Mars, we have to find water in order to claim life. And that may not be life, but nevertheless. So, fundamental. Common to plant, animal, human life. It conveys disease, and pure water, as I keep reminding all the medics, is civil engineers have done much more for human health than all of modern medical science. Simply providing clean water and handling sewage, etc. A lot of healing traditions. The Russians, the Chinese, the Indians emphasize drinking water. And Indian water purification therapy, very important, and including urine therapy. So water is a very key, the most important single substance for health. The NIH has zero money devoted to water. How about that? Okay. What are the facts? Water has been known for intimate connection. Getting pure drinking water is our best thing we can do. We've doubled our life expectancy by doing that. And it isn't from the health aspect, from the medical, all the little pharmaceutical aspects.
Right.
More facts. We'll come back to this at the end. Ultra dilute. You know, when homeopathy is treated, we always talk about ultra dilute dispersion or suspension or whatever. That means, you know, it's way, way, way dilute, millions. You've got to start at, say, 1 part in a million or something. Now, very interestingly, in the last few years, there's certain other ultra dilute colloids, especially that of silver, have been shown to be extraordinarily active in the petri dish. In homeopathy, we can't show it in a petri dish. And the big advantage of using this argument is, here is a similar ultra-dilute colloid, sol, whatever you want to call it. Aqua sol is the proper term, water sol. And that, in the silver colloid, which you'll see right at the end, has been demonstrated in another long paper of ours, which you will also see in your references.
Great, great.
But now what that suggests, and we are very hot on this right now, what about regular drinking water, regular stuff in the spas, in the Ganges River, etc.? Those waters are analyzed by very stupid chemists. I'm a chemist, remember, so I can say that. They give you the chemical composition. That's not important.
Right, right.
The chemical composition includes two kinds of things. One of the impurities could be in solution. That means the elements are distributed in the liquid phase. But the other part is in little dots of solids. You know, when you see a slightly blurry water, that is what it is. It's a sol, a dispersed solid present in water. And now, because of the silver work, holy cow, maybe other elements, other minerals, other phases can also have healing properties. And at the end, I'll tell you of a new revolutionary discovery which makes this even more likely. So we now look at different waters, spas all over, Lourdes, the Ganges data, and homeopathy. They all come under ultra-dilute dispersions or sols or colloids. The colloid word has got, some kind of homeophobia also.
Right, right. Colloidal silver, which you can pick up at health food stores now.
Exactly. No, but there's the specific ones that we have worked with. There are many kinds of silvers. The only ones we work on are pure metallic silver in pure water. So one has to be a little careful about that. I'm not saying the others don't work, but that's what we have presented data on. Now, here is water as a major key. Now, the next sentence is the most important sentence for you to grasp. A phase, that means any material, liquid, solid, anything, is defined by composition. That means it contains H2O, but it's also defined by structure. The structure is the most important descriptor of any phase, solid or liquid, not the composition. Now, that's statement 1, which we'll justify. Statement 2 is, water is not homogeneous in either. It is not just simply saying H2O molecules. I've just got a basket full of apples. I've got a basket full of H2O molecules. Wrong, wrong, wrong. And that is what the chemist has treated it as. A basket full of H2O molecules. That's absolutely fundamentally wrong. And that is where they went astray. All right, now let me tell you the data, right? Solid water, that means ice, right? If you freeze it and you squeeze the ice, it changes. You squeeze it a little more, it changes some more. You heat it a little, it changes some more. So we know that in solid water, we have at least 12 different structures. Holy cow, without any shadow of doubt, nobody contests it. We have it by X-ray diffraction, and we know exactly that. Now, our conclusion from our work is liquid water is equally, we have an equal number, something, large number of different structures. That is a fundamental statement of our assertions. And how does that happen? These are big long terms. Oligomeric means small clusters of those H2O molecules. And that clustering or structure varies with temperature, with pressure, with pH, EH, that's the oxidative potential, with a magnetic field. You know, all this stuff about do electromagnetic radiations affect, the cell phone stuff and all that. And those are the questions. Dr. Tiller's work shows that they do affect the structure of water. What about electric fields? Well, the very recent work,
right,
absolutely major effect on the structure of water. We'll not show the data here, but I'll refer you to that. The other is a strange word called epitaxy. If you see at the bottom, the second line from the bottom, there is a term which I introduced you to. Epitaxy. Epi means the surface or skin, and taxi is a structure. So the structure of the surface is transmitted into the nearest liquid that it touches. So if I take a certain structure and put it near any liquid, whether it's water or not, that surface layer is changed. And I don't mean just a couple of atoms. I mean a micron thick even layer is changed. This is well known in material science. The word has never appeared in a chemistry student's biography or bibliography or anything. So in material science, we use it commercially every day in the high-tech world. So it is extremely well known that what? I can transfer the structure from a solid to a liquid without transferring one atom.
That
Isn't that amazing? That you can, it's like a rubber stamp, right? Your rubber stamp is not transferring any rubber. It's taking that ink and putting it on there. But the structure of the letters which form is done simply by stamping. So epitaxy means rubber stamping. I mean, use it as that. It's a rubber stamp, okay? So we can now say the role of liquid or solid additions in homeopathy could be critical. That is the argument a homeopath can use. We are not doing this for homeopathy only. It works for everybody, including the silver colloid people.
Right.
Okay. So what is then the structure of water? Those are things it's not, and so on. First, it's not the spherical chicken. You know, all physicists say, okay, let's make it a little simple. Let's call it a spherical chicken. Well, chickens aren't spherical. Water is not H2O. It's not a spherical chicken. And it is not, I'm using Professor Zakariasen, a good friend of mine, used to be, Zakariasen's random network, a homogeneous structure model. I'll show you what that is in a minute. It's much more complicated. And it's just, if you look at bullet 3, if you want a scientific summary, water is a statistical distribution of different size oligomers, clusters. Each one has a different hydrogen bonding. Each one has a different structure. That's what it means. You'll see some pictures of this, arrangements which you'll see, which are all mixed up in the liquid water. This distribution, remember I said statistical distribution on bullet 1, bullet 3, bullet 4 says this distribution is highly sensitive to temperature, pressure, and a lot of other vectors, magnetic field, and so on. And if you want to think of one example, which in our human experience we encounter, it is that water has the highest density at 4 degrees. Otherwise, all our lakes would freeze and there'd be no fish in them. The fish all head for the bottom. The ice goes to the top. The density of the liquid layers is always at 4 degrees. It does not freeze, and that's what saves a lot of life in very cold temperatures. And you see that again about, we have 10 crystalline and many non-crystalline structures. Now, interesting one is the third bullet from the bottom. Water can be made into a glass. This is very important. It's not only crystalline. If you cool it rapidly, like you can do this very easily, take a little bit of water and take a dropper and drop it into liquid nitrogen in a little dewar. It's not crystalline. It's a glass, just like the glass in your window. So that is a new thing that most people don't realize, that you can make non-crystalline solid water. Okay. So this is a perfect, the people say there's no different structures. Not only can we have 10 crystalline structures, we can have 3 or 4 different glassy structures. So the whole idea of a single thing called water, we got to just use that as an argument against anyone challenging homeopathy because, the water is all the same. No, water is not the same. So relation to homeopathy, the last bullet, changes to structure, not composition, may be the key. And pressure is during the succussing process. You know what every homeopath knows, that you shake and bake that mixture. And Hahnemann had that very special way of doing it, and every company does it in a different way. But you sure as heck are shaking pretty rapidly, and you think, well, you don't think about the pressure that you generate. And everybody says, that can't be very much. Wrong. Pressure is force per unit area. And if you think of a little bubble or a little droplet of water and just take the numbers and do a little calculation and use any force that you're applying, and imagine 2 bubbles are running into each other, and you can see that you get pressures of easily, and we've done this with solids, and we've shown the numbers are 10 to 15,000 atmospheres. It's not a small pressure. Everybody is surprised. Well, they can go read our papers, and these are cited, of course. So these are papers in Nature, a couple of papers in which if you just grind something, when you're grinding something in your mortar and pestle to put into your food, you generate pressures of the order of 10 to 15,000, maybe even more if you're a strong-armed character, atmospheres. That's a huge pressure, well in the range where we get those high-pressure phases in the crystals. So now we're not talking about some small change, it's a whopping change in the homeopathic process of succussing. Now you can get the epitaxy from the remedy that you put in. If you put in Nux vomica, you have little Nux vomica particles. If you put in, Nat Muir, you put in some sodium chloride, those can all leave imprints on the water. That's by epitaxy. So pressure and epitaxy can have big changes. Next one. Now we're going to get a little detailed and esoteric. This is what we call the random model, random network structure by Chakrayasan. And all he did there was to take a crystal and move the things away from a regular array. But he said, look, it's all homogeneous. Any part of this structure can statistically look like any other part. I mean, that was his model. You just take a crystal and move some things around a little bit, get them out of place so they don't diffract, but that's what glass is. And that is still taught, unfortunately, in hundreds of chemistry places and so on. That's the structure of glass. It's simply wrong. It's simple old-fashioned stuff which the professors, when he was a kid, they used to teach that. So, of course, he passes it on to his students. But let's look at what the reality is. This is work about the middle of 1984.
Figure 2. Why don't you tell me on figure 2?
Oh, I'm now on, there's two figures there. You see the one with two pictures, and then it's called figure 2 in the legend. Yeah, I'm sorry, it's called figure 2 because it was taken from somebody else's paper, of course. Now, look at this. This is transparent glass. Imagine you're looking through a window, right? This is how it looks in a transmission electron microscope or scanning microscope, one or the other. This is TEM. Direct evidence that water is not homogeneous. Now, please look down at the B, the one in the middle, the picture in the middle. First, you see that you've got a very big cluster, then some littler clusters. Inside each of them, you see, they have broken up into another set of clusters. So there's really 4 different structures. And if you didn't have a different structure, it couldn't break down. You see that the arrows are 1 micrometer. So that's 10,000 angstroms. And these are, say, 1/10 of that. So that's about, 1,000 angstroms, 100 nanometers or something. And inside those are the little fellows, which are about a few nanometers. So we are really talking direct evidence. No ifs, ands, or buts, folks. That's what a glassy liquid can look like. Not that this is water, but this is showing that typical liquids like that with covalent bonding turn out like this. So what have we established? That the probability of having a heterogeneous structure in water is reasonable, and nobody can say that's an outlandish idea. Now, this, I'm afraid, is even more scientific. This is the thermodynamic version. This is the...
Tell me change slides.
I've changed slides to figure 3, and you're now looking at a bunch of what we call phase diagrams, and this is actually a very interesting paper, which is 2 pages long, which I published in 1960. It's amazing how important it is. That paper, Professor Poray-Koshitz in Leningrad, the one I showed you as figure 2, he cites this as one of the most important papers in science. It is a prediction that very many systems will show that kind of behavior. If you have a curve which is kind of showing that little bending, then you better watch out in that liquid. Because under that liquid, you see that little hump, the dashed line. That tells you that that liquid is going to break up into those different regions. So this is a pure thermodynamic argument to say, well, not only what I'm saying is reasonable, but it's almost demanded by thermodynamics. But that's getting away from that's all detailed science nonsense. Now, this is worse nonsense, but it's an important fact. This is the same kind of phase diagram. It's called figure 4. It is a pressure temperature diagram. Please ignore most of it, except that this is for sulfur, molten sulfur. Molten sulfur resembles water in a very important respect, that it is a covalent liquid. That means strongly bonded liquid. Like OH bonding, it's a strongly bonded liquid. Now, if you look at the left-hand side, you see that you get a lot of crystalline sulfurs at the bottom. There are about 10 or 11 of those also. On the right-hand thing, I want you to focus only on the upper half of that picture, where you see things like, I don't know if you can see them, C, B, D, E, and so on, different liquid ranges. This was unheard of, that you can get different structures in liquid. This is the first paper in thermodynamics showing the existence of these. This was published in Nature, something like that, Nature of Science, in 1972 or 73. And we published several of these now, which you'll see in a minute, and nobody's ever challenged it. So it is an accepted fact now that you can get several liquid structures in many different materials. Very similar. Here's another one, which is glass, which is diamonds. These are actually what we call glassy carbon, carbon made into a glass. Just like water can be frozen and made into a glass, you can take carbon. And what they find is, you can see the letters G and T, that it is made up of little regions, some of which are like graphite and some are like diamonds. So here we have different structures in a glass, looking transparent, shiny black glass, just like water, if you freeze it or something. So we're establishing that it is very common to have different structures of similar liquids. And now comes the kicker, that while we were writing this paper, a man called Kawamoto in Japan actually did the structure of water in the same temperature and pressure regions that I was showing you a minute ago. Figure 6.
Yes.
The pressure is, 1 gigapascal means it's about 10,000 atmospheres. 2 is 20,000 atmospheres. So remember, your little shaker can easily generate these pressures. You got it?
Got it.
This is not some absurd pressure. So these are very similar to the kinds of pressures. Now, what he's shown is what he calls sparse and dense, 2 waters. Well, he probably didn't have my thermodynamics courses, but he should. We know now that there must be a line that emanates between 5 and 6 and 6 and 7. So there's got to be lots of lines like we had in sulfur and so on. So we have nailed it down, not only by extrapolation, by saying from our work on sulfur and selenium and so on, but here comes Mr. Kawamoto in 2004 and does it in water. End of story. There can be many liquid waters, absolutely proved now by the Japanese workers. All right, so now instead of all that crazy stuff, I give you a nice figure 7. Figure 7 is a cartoon version. It's a take-home kind of thing. I've got a new one of clouds in the atmosphere or something. You see the little spherical areas or pseudo-spherical areas. This is a paper in 1971, long before I ever thought about water. But you'll see that that actually water is mentioned in that thing. You'll see examples. Strongly bonded liquids, sulfur, water, and polymers. So this was in 1971. We were saying that the structure of water will look like this. We didn't know what those clusters are. Nobody knows them now. But they're different. That's all you have to say. They're different. And if you shake them, they'll be different. That's all. Now, this is figure 7b. This is a paper in 1998, some 25 years later, by my good friend, Professor Bockris, one of the great electrochemists of the world, and his book was ready, and he shows us, and you now notice these little big blobs and little blobs and big blobs and little blobs. These are all cartoons, but it is conveying the fact that we're saying there's different structures, and he's got little unassociated molecules, which means the monomer, H2O. Okay. Now we go to what the chemists show in their typical talk about the structure of water. If you go to Martin Chaplin, that's right at the bottom, you see the quotation by Martin Chaplin, professor at London South Bank University. He is, without any ifs, ands, or buts, the guru of chemistry of water. He's a very fine gentleman, a real scholar and gentleman, and his website has about 6 million hits. So everybody looking at the structure of water should open up Martin Chaplin. You get these beautiful pictures, and regrettably, that's all they are. Not with respect to the structure of liquid water. Now, these are molecules. If you zap them up in the vapor, they can calculate these lovely shapes. these are pure tinker toys which you can stick together in different shapes. And this shows you the probable shapes and the different permitted shapes of water molecules. Very important. Not liquid water. These are water molecules.
So, Dr. Roy, that would mean that you could have several of these different structures all occurring at the same time in one glass of water, say.
Absolutely, and we don't know how much of each, and we don't know which of those molecules are present and how they will change with the pressure. These are the little units I was showing you in any one of them.
Right.
Much bigger. You see, I'm coming up to bigger units. That is exactly the point, Jenny.
Great.
Let me show you another one. Now we're getting some monsters, right? These are monster tinker toys. Yeah. This is figure 9, and you'll see that look at those. Some of them have more than 200 water molecules. I think the one on the right is, and they've got a certain symmetry. This is really, you can make up a lot of these, and this is what we mean. Like if you're under pressure, maybe those form, right? Or maybe the other one goes the other way. We don't know whether there's more little ones or big ones. And nobody has pretended to decide yet which ones are present. Most of the oligomers, when we use the word oligomer means a small number. So these big molecules, probably, we don't know that, but probably there's not a heck of a lot of them around. But these are the ones which you will see in Martin Chaplin's papers, in his website. He really is an invaluable colleague because he does this very hard work of collecting all the data in one place on the structure of water. But he does not talk about liquid water. Now I'm going to switch and show the difference and the difficulties we have with deciding.
Figure 10.
Figure 10. This is now figure 10. Between crystalline matter and liquid matter, or glassy matter. It's really a different ball game. In all crystalline matter, we can determine the structure within a thousandth of an angstrom. That means a 10,000th of a nanometer. That precisely, we know where every single atom is. Now they're vibrating, of course, but we know the average position within a 1,000th of an angstrom. And you can see we have different shapes. These are the little shapes that we saw in the other thing. This is a material called barium titanate, the most important dielectric in the world. In every computer, this is what you use. So look how precisely those are arranged. They don't move from that. That's exactly where they are within a 1,000th of an angstrom. So you can say to me, how come you guys can't do that with a liquid? Because they're disordered. They don't have these positions which we can only determine by diffraction methods. X-ray diffraction, electron diffraction, neutron diffraction. What does diffraction mean? Diffraction means you've got to have a periodic arrangement to make those, whatever radiation you use, diffract, interfere with each other. If they're not periodic, they won't do it. So in these places, because they're fixed, they diffract. So we can use diffraction methods for structure. And that thereby hangs the unfortunate part that we can't do it for liquids. All liquids. Everywhere. So that's why we can't do this kind of precise structural thing which we can do for every crystal, several 100,000 of them.
So
here's making the other little units of that structure. It's very figure 11 with all the different colored tetrahedra, octahedra, and dodecahedra. That means with 4 nearest neighbors, 6 nearest neighbors, and 12 nearest neighbors. So those are the little green, the tetrahedra are yellow, and the octahedra are mixtures of yellow and purple, and then you have the green one, which is the dodecahedra.
So, Professor Roy, you could know what I'm understanding is that by looking, you don't have the technology to take that kind of a clear, precise picture of liquid the way you can of the crystal.
We can't do it because to do that, the boundary condition, as we call it, it is necessary that all the atoms be in fixed positions, and in a liquid, they're not. Right. They're roaming around, and therefore you can't get that. You got the exact point, Jenny, that in fact the fundamental difference of the liquid and crystal, nothing to do with water or anything else. In the glass is the same. The glass of your window, we can't do it either. We can't use that. We have to use transmission microscopy or spectroscopy, and then we get into statistics, as you will be seeing in a minute. So that becomes a problem. Now I'm going to compare the two. You will hit it right at the point. Here is a picture. This is figure 12, and you can see here, nowadays we are so darn good, we can actually see the atoms. This is a transmission microscopy, high resolution, and we can see every single atom. If you look at what's called the matrix zirconia grain, you see the array, one dot after the other, all lined up. We can measure those babies. You can see 5 nanometers. You can see those are sub-nanometers. We can look at every single atom. And we can now even focus in on one atom and find its chemistry. But now look at the middle, where that red circle is drawn, where the 3 areas come together. It's all muddled up, and it's glassy. We now can look at that and blow it up. In the top right-hand part where it says 1 nanometer, we can actually show that the liquid part, the glassy part, because it's frozen to a liquid, you can see there's no lines in it. They're not orderly. In fact, you see, there's again the different size bubbles. I mean, little regions. Big bubbles, little ones, and if you really look, there's some gray areas within the white area. So this is exactly what we said. They separate out into different size clusters. Now that's direct proof, no ifs, ands, or buts. That's transmission microscopy. You're looking at the baby right down to a nanometer in size. I mean, these are now atoms, right? You're talking about atoms.
Right.
That 1 nanometer is about 10 atoms across. So, but the other ones are about an atom each. So we are now able to show that glasses, in fact, are kind of mixed up, muddled up. They're not orderly. They're not lined up. And so we can do this with water. We are trying to do it at Arizona State. It's an extremely difficult thing because you've got to freeze it at liquid hydrogen, liquid helium, and then take it into the microscope, and then in the microscope it's evaporating. You've got to do it very quickly, and maybe you'll see something. And the worst part is the contrast with water is so small, because it's only hydrogen, oxygen, that we don't know what we can see. We're just trying that now. You'll see one picture from that. Okay, now this is coming back to water and saying, Figure 13, the fact that in reality, the ordinary water has all kinds of different properties. Now, these are 3 different properties measured: isothermal compressibility with temperature. Notice the temperature, and you see there's a change, kind of a dip, a minimum at 319 Kelvin. And the next one is isobaric heat capacity, different properties. And that has a blip at 308. You go to the next one, which is thermal expansion. Pretty important, right? It's completely different. The change is in a different direction. And then it has a maximum slope at 277 Kelvin. Now, we know from the first law of material science that structure determines properties. So every time you see a property changing like that, what do you know? You're changing the structure. So what's the big deal, for crying out loud? Water changes structure all the way through. This is ordinary room temperature. We're not talking about some esoteric temperature, esoteric pressure. We are talking about room temperature. When you take it out of the freezer, this is drinking water temperatures, right? So we are saying that those properties are different because their structures are different. This is proof. It's a big shock to the chemistry community. They simply have ignored it. All right, so much for the pressure and temperature possibly changing structure. One more thing about epitaxy now, right? Figure 14 is the template. You see on the top left-hand epitaxial substrate, right? Any crystal. The liquid just above it is changed, and you can force that liquid to crystallize with the same structure as XY. So I have an AB liquid, I put it above an XY solid, and guess what? The AB liquid crystallizes like XY. That's weird.
So it mimics the structure of the thing it's put up next to.
Exactly. It mimics the structure of the thing that it is in contact with.
Rubber stamp.
Rubber stamping, the good old rubber stamp, right? And, you can do that with, to give you a very dramatic example, is graphite and diamond, right? You can even make something go towards diamond by simply putting in diamond substrates. You put in a diamond pattern and it'll become a diamond. Guess what? So, what we are saying there is bottom right aqueous solution next to a homeopathic remedy, then that liquid next to it can. We don't say it does. We don't know. But there's a plausibility argument now which we introduced that's saying it could, in fact, be changed. The liquid next to the remedy can be changed. All right. Now we go to the third argument we introduced in this paper. Figure 15 is the possible presence of nanobubbles. Now, when I first started talking about, people say, forget nanobubbles. How do we know there's nanobubbles, right? Well, imagine you're shaking something. You can see the bubbles, right? But you keep on shaking. Well, you know that there'll be a distribution of bubbles. There'll be big bubbles, middle bubbles, little bubbles, very little bubbles, micro bubbles, and nanobubbles. There's bound to be some distribution. That's thermodynamics. I mean, you've got to do it. Shake them up, you get little fellas. Now, little fellas are more stable than big fellas. They don't want to come up as fast. The big bubbles come up to the fire quickly, then the little ones come a little slower, and the littlest ones may actually be permanent. Can you imagine? That's a colloid. Remember that we have silver colloids? Silver is pretty heavy, and air is pretty light. But the difference between silver and water is a heck of a lot more than between air and water. So if silver can be suspended, air could be suspended in water. No big deal. It's lower, but it doesn't matter. So the possibility, of course, is always there. Question is, do they exist? Here's a paper now in PhysRev Letters, which is a very high-tech journal. Irregular nanobubbles. They actually took a picture with a transmission electron microscope, with a scanning electron microscope. And there you see, these are little fellows, not too little, at 0.2 micrometers. So there they are. You can see bubbles surviving. And remember, if you can see those, they're little fellows you can't see. So, yes, in the succussion process of homeopathy, you absolutely, certainly develop nanobubbles and microbubbles. What happens to them? God knows. But again, all we are doing is introducing a plausibility argument that the homeopathy process, I use the word process, it's a complex process, introducing shake, dilute, and you do this. So that process is bringing you to these interesting shapes. Now, I better move on now. Now, these are changes with magnetic field. Dr. Tiller has shown in his work that if you put a very small magnet, like your refrigerator magnet, you can get the pH of water to change. So, and now we are saying that we can we actually change water, and what shall we look at it with? I will introduce figure 17, Raman spectroscopy. What got me interested in this field actually was this particular figure. This is the Qigong master, Dr. Yan Xin, whom I know rather well. He was a personal physician to Deng Xiaoping, the Prime Minister of China for many, many years, and he was changing the water from 7 kilometers or even 2,000 kilometers, 6,000 kilometers away from San Francisco to Beijing. And so look at the difference now between the top left and the top and the bottom left. Is that a change or what in the Raman signal? I said, holy cow, either this guy is drawing him in and making them up, but the person doing this was the head of the physics department at Tsinghua.
And so he's changing this, Dr. Roy, by, sending chi energy.
He's sending chi energy from a distance. He first did it at 7 kilometers away, never in the same room even, and then he did it across town, then he did it from San Fran to Beijing and so on. So it really is, I want to go into more details. So that said, is water that changeable, that intention? These are relatively weak vectors. If you could do that, now I don't know, I just assume nobody's cheating here, and I said that is certainly very interesting. So then what we did is to get this image. This is figure 18, and you'll see this is what we did at Arizona State. This is a nice model. See the little background of the little molecules. Then you have B's, and you have C's. This is actually ice cream. And we said, we froze it, we put it in a cryo-TEM, so to show that we can do it. It isn't water, but what the heck. We can freeze ice cream, make it down there, and we can actually, well, you can see the fat molecules, of course, but it does show that we can get that. So this is the kind of heterogeneity you can get. So I'm going to leave you with this picture. This is now a little more high-tech. Figure 18. 19. The cartoon version of what I presented. You see the different molecules which Chaplin has. I brought in a mixture of these. This is completely imaginary. But this is the figure you should take home for you to say that's how water really looks, folks. Different arrangements of different clusters all the way through. And that arrangement is changed by all these things we talked about. First, epitaxy, second, pressure, and third, dilution. The 3 or 4 different ways in which you can change water. But that's the structural thing. Now, we better move to what about the facts ignored by critics of homeopathy? The enormously complex structure of water. First one, they ignore that. Second, they ignore the role of epitaxy, which means it's irrelevant. They don't have to be present anymore. Remember what we said. Epitaxy stamps the liquid, and the rubber stamp goes away. You don't need it. Major changes with pressure. They ignore that. Now, the question is the kinetics of change. Okay, people will admit maybe you can change it, but does it last? We don't know. How long does it last? We don't know. Then, a very interesting one, influence of magnetic and electric fields. No doubt now, I will be saying a little bit about a very recent work in the last 2 weeks, 2 or 3 weeks, about electric fields and how much they can change water. How much? We'll say a little bit about that at the end. Now, new experimental tools. So, this is what the critics have been ignoring, and we should not anymore let them get away with that. That's for the homeopaths to make that case. I'm a neutral observer on the side. Now, what many scientists are opposed to the various therapies, their model for the structure is primitive. It is based on high school chemistry, so we should stop it. Chemists think of water as a homogeneous beaker full of 3 angstrom-sized balls. Material scientists, with a little knowledge, we conjure up their minds about the structure of glass as frozen like a glass. No, it is more complex than that also. So what we've been doing is, at Penn State, state-of-the-art materials research on living systems. And so all we can say is we're taking our tools of the trade to this issue. Now, we do nothing clinical. We know nothing about the efficacy of homeopathy. And so to do that, we've been using a whole set of tools. It's very important. My personal approach to this is you can't fix it with one tool. So we're looking at a whole lot of tools. Of course, we don't have the money. I see there's a misspelling there. Acoustic is spelled wrong. But I think that we triangulate. Number 0.3 there is we triangulate by correlation of anomalies across techniques. It becomes essential for us. And that will be our approach always. All right, now we're going to give you just a little bit of data first on the silver colloids, and then I want to move very quickly to some of our data on homeopathy. Okay, first thing, this you can't read it. This is antimicrobial organism on top, but it shows that a silver colloid, a particular one which we cite, at a percentage of 1 part per million silver atoms in water. 1 ppm silver in water molecules. It is as powerful an antibiotic as tetracycline or flaxin, penicillin G, all those things and so on, erythromycin and so on. Typical antimicrobials are compared, and we see that silver water, which is the last one, ABL, high voltage dispersion, is just about the same. That's absolutely staggering. Okay, here's a gadget to make it in. You don't need all that. This is what this particular manufacturer sells. We don't think it's limited to any one manufacturer, but it is certainly silver in water. If you go there, ASAP is, I don't know what it is, American Biotech Labs is a company. Now, typical particles, you see are 30 nanometer particles. These are when they're dried, of course. And this is, again, you look at the high-tech machinery, it tells you, look at those atoms. Each one is a silver atom. But the blob is about 30 nanometers across. The diffraction tells you exactly what it is. Tells you it's a metal. It ain't something else. And then we use different techniques, as I said we will, to look at the water layer on top of that. See the water layer there? And we call them different kinds of water. And here we start looking with figure 6.
I'm just going to catch people up. I think we're on slide 36.
Oh, it's called 36. Okay.
Yeah.
38 on my thing, but...
Okay, 38. You're right. I'm sorry.
38. Okay. Slide 38 on the side, and it's showing you the difference. So that's all you need to look at. Same instrument, pure water versus the colloid. Look at the difference. Here again, you will notice the same kind of thing. This is 39, figure 39, and figure 6 and figure 5 at the bottom, so it's confusing. On the data themselves is figure 3, 4, 5, and 6. And all I'm going to tell you is it's easy to spot the difference. Remember, there's only one part of silver in all the water. It makes that much difference. And this tells you that you better watch out what you're doing, because if you have a Raman spectrometer with different radiations, that shows differences too. And that brings me to the point I want to end on before I leave, is a new, very new work, how radiation can change the structure dramatically. Let me come back to that point. Here again is the same stuff on silver dispersion, comparing Raman spectra with different instruments. We've got the instrument on the left because you can see it's a little better. You can go inside the water. We stick the probe inside the water. All right. I don't think we need to mess. Okay, conclusions. Classical approach is too narrow and one-dimensional. Size and shape of the building blocks tells you nothing about the structure. Material science establishes that. This is the bottom line, literally. The Avogadro limit argument, universally used against even the plausibility of homeopathy, is simply wrong. Nothing. Stop there. Nobody can challenge that statement. And I think it should be widely used by homeopathic proponents to say, okay, let's move on to your next point. Let's look at whether it works.
Great.
Okay, I think, now let me just, I'll stop there, and I want to tell you about this new, very interesting work by a man called Kanzius. Many of you have seen it on the web. It's got 2 million hits on YouTube. Of a man in Erie, Pennsylvania, who shines a beam of radio frequency waves. That means, just like your shortwave radio. That frequency, he's a television station owner, and he used the same waves he's using it for cancer research, but accidentally he exposed salt water to it. And it looked like it caught fire. And it is. He essentially broke up water into hydrogen and oxygen, not with light. If you're a light bulb, that light bulb is 1,000,000 times stronger light photons. The energy of those is 1,000,000 times stronger than that shortwave radio. With that little electric signal, electromagnetic wave, you can break water up into hydrogen and oxygen. He can light a fire out of the hydrogen and make water. So there's lots of interesting implications for energy and chemistry and so on. But for us, what it is telling us, something very profound, that little radiations even can affect, very weak radiations, can affect the structure so far as to destroy it. It destroys the structure of water with a little radio wave. Now take that and go home with it and say, okay, we've been too naive about water. And I think you should follow this stuff on the YouTube. And I'll send you a link, Jenny, and you can forward it if you wish.
Great.
Okay? So that's my story, I think.
Fantastic. I'm going to open the lines up here to questions. So I'm going to actually press it.
Jenny, let me just finish off. I said the next set of slides which they have is the same kind of analysis of the homeopathic samples, and this is what we conclude, right?
Okay, great.
They're all there, but it's more important to show what we have shown. Our data suggest, and we don't prove that it works now, we don't know anything about homeopathy working, that the remedies are different from the starting solvent. Second, that 6x and 12x and 30x are different from each other. So whatever they're doing something which makes it different. And third, the structures seem to change. They change with the remedy materials. Now, that is additional evidence that there really is something different about real homeopathic remedies. So we've applied that structure water concept now to the homeopathic stuff. There's a lot more data, and rather than get into all the details, you can follow our literature, which is proving just those 3 points. Not that it works, but that the liquids are different, and so it destroys the argument that it's just the same old stuff.
Right. So they can't say there's nothing there.
Can't say there's nothing there.
Right. And I'm going to just unmute this line. 1 moment. And I'm going to open up. Is the moderator on the line? Or Melissa can check to see if...
Here. So just to ask questions, you just need to *0 and state your name and where you're calling from, and the operator will let you in for the question. I actually have a question for you, Professor Roy, about the epitaxy. Another way to look at it would be this transfer of information. Is that
the right terminology? It is transfer of information. Correct. Absolutely. You got it.
So as a human being who's taking a homeopathic remedy who is mostly water anyway, then that's another possibility. I mean, this is completely hypothetical, but of another form of transferring information.
Sure, of course. That is precise. You've got it.
Okay.
That is what happens. We assume if the homeopathic remedy has got some information, then that remedy can transfer that in some way. I don't know what, but I think by and large, that is precisely the argument.
And it's from water to water in some form.
But some water to water in some form. Now, when we say we are 70% water, 60% water, of course that water is combined with everything from DNA to the blood to all that kind of stuff. And all that will need to be studied. That's why I think they should have a whole institute in NIH called water water-related research. Anyhow, yes.
But you're claiming this is true for any liquid too, right? That this type of epitaxy is happening in any form of liquid.
Of course it is. In
So
solid
it's not just water.
We actually have shown solid-state epitaxy, but liquid epitaxy is much more common.
So this, in a way, gives us almost a visual representation, even though it's in this tiny way of using microscopes at this time, of how something could transfer information from a homeopathic dilution into the human being. Is that right?
Now, how you go from the homeopathic thing into the human being is the next step.
Okay.
It gives you scientific tools.
I see. But the fact that it will form a change from contact with another molecule of a liquid form, we know that that's where that transfer of information occurs. Is that right? Do we have enough knowledge at that point?
That is right. But now remember, when you swallow that, God knows what's happening inside your body and is being chewed up and dissolved by your stomach acids and so on. So somebody could argue that. So maybe one should bathe in homeopathic remedies or something and get it in through the skin. So how that transfer is affected, and that is an important question, in fact, as to there is a lot of that stuff in spas and so on. But from there on, you've got to make another hypothesis on how you get it into the system and how that transfers. But like the silver colloids, right? Remember that. That's easily proved. This dilute sol with a different structure definitely has, in a petri dish, you can do it tomorrow morning, you can stick in some E. coli there, add a drop of water, which has been structured with silver, and it kills all of them. You take away the silver, nothing happens. So you can say the same thing with a homeopathic remedy. What can it do? If one could find, now this is the kind of research which, let me tell you what the advantage to the homeopathic community is. First, it's given the manufacturer the most powerful quality control tool. I mean, this is very important. To improve the quality, they can check, do I have the same thing?
Right.
So that's one. Second one is it gives them the kind of thing which you've just indicated, a new vector for research to say, look, we ought to be doing this kind of stuff.
It's interesting, Professor Roy, that, in Hahnemann, in the last edition of the Organon, the conclusion he came to at the end of his life was that remedies should all be dissolved in water and administered to the client in a water solution. That was his final work in his lifetime of study.
That's interesting, yeah.
And I think I know myself as a homeopath, and I think many other homeopaths, I never give people just pellets. They take the pellet, they put it in water, stir it up and dissolve it in water, and then take sips of this solution of the remedy.
Okay, yeah. That's the kind of thing which ought to be really looked at very hard, yeah.
Yeah, very interesting. Melissa, do you have anybody line for question, or I have some questions to ask?
Okay. We have a question coming from Tim in Massachusetts. Tim?
Hi. Thank you very much for that presentation.
Yes,
just in follow-up of what Jenny was just saying, most homeopathic remedies are traditionally given actually as, the sugar pellets. So do you have data that, you can take a substance, make a change in water, and then add that back to the sugar or some pellet form so the water then dissolves, and then there would still presumably be some residual influence left over?
We have no data, of course. We have not support. We don't have it. This is the goodwill kind of work that we've done. No, absolutely. We have no data, of course. But that is the line of work which we've opened up. I think the homeopathic community will have to man the barricades and get on with doing this kind of research. And not that I'm asking to do it, but I'm saying that it has opened up a whole new train of research, and which they can go to NIH, they can go wherever, and ask to do that kind of stuff. Yeah.
And I was trying to look at those last, 3 or 4 slides that you didn't really go through.
I didn't want to. Yeah, I was getting on.
And some of those refer to 60 or 6X and 30X, and it looks like the 30X, the bars go higher there. For example, Figure 4.
Yeah. Let me explain those. Just to be quick on that. The reason I didn't go to that is the only point that we make is there is a delta term between the 6X and 12X and 30X and so on. And actually the error bars and the statistical spread shows that the quality control from the manufacturer is poor, but yet there is a statistically significant difference between them, and we showed even the full range of errors, full range of data. So I think that all we establish is there is a difference between potencies and there is a difference between remedies. That's it.
But is the 30 potency there, even though it's more dilute, showing a stronger effect?
No, see, stronger, weaker, we don't know what it means, that stronger or weaker. It is more different, and whatever the hell that means. So all you can take home from those data is, here is a new tool which can help you answer the questions you are asking. And you would have to do those experiments, whether you want to do it by dissolving the solids or whether you want to say, is it stronger? Here's the first thing you need to do is get 6 manufacturers to give you Nat Muir and 30X and see if they're the same. And then you want to know, well, maybe they're different from each other. And maybe they could do them in different days. Are they similar? This is you've got a tool. I mean, the homeopathic community has a great tool now.
And when you are looking at the differences that show up at these very, very minute levels, one of these things is the ultraviolet light spectra analysis.
Yeah.
So what are your impressions that are the areas that are ripest for picking up the sensitive changes here?
Well, actually, you'll see some more data. I think of first the tools. The best tool right now, single tool, would be Raman spectroscopy, because that looks not at the nearest neighbor, but the second nearest neighbor and the third nearest neighbor, because that's where the changes are. The water molecule's not changing much, and that's what's wrong with NMR alone. So we need to look with several tools, and you should not try to answer all the questions definitively like, what is the change? Hell no, we'll never know that. It'll take us 10 years. So which molecules are there? I mean, look, up to now, nobody knows what's there. So we should not ask the kind of the last question you want to know. You want to ask the question which you can answer with the tool, which is, am I different? And is what I'm doing changing it? And does Boiron supply the same thing as Hahnemann supplies? Those are the kinds of tools which you can answer. Then only you can move to the question of, like the one somebody asked, if I dissolve it in water and drink it, is that the same, right? That's a very important one. That could be answered, perhaps. So I think what we have done, and I want to show that we are very limited. We haven't done much work. Nobody's paid us. So I think by and large, it's a beginning, not the end.
And I'm sorry, one last question. A big thing about homeopathy is resonance. You get a very, very small amount of substance, but then it has an effect on the entire body. And there's this thing that there has to be some resonance between one thing and another thing, even if they're actually not even touching. And I was wondering if your data, when you're using these very, very sensitive instruments, can show resonance between what's happening here and what's happening over there without the touch. Aside from that, chi experiment, do you actually see that at a chemical level too?
And that is much more relevant to what I alluded to at the end. This new work on the resonance with the radio waves into water. You're specifically, and you should be following that very carefully. It's absolutely new. There's nothing. The only papers will come out from my lab, and so on. It's the most interesting thing that you can do with a very weak wave. Now, when you can do that, then you can ask, when these healers claim to have changed by holding the water in their hands, now Stefan Schwartz's work, that becomes very interesting. He used infrared instead of Raman, and that, again, you say, aha, maybe this is resonance, because that is, in physics, what we call resonance, right? It is a resonance phenomenon. The person's name that you should write down is Dr. Juliana Brooks, B-R-O-O-K-S. Juliana Brooks, and she was at Ohio State Medical Faculty. She's now president of a company in Baltimore, near Baltimore, and you should follow her work. It's all about resonance. She's a medical doctor in all kinds of changes, and I think it is as close. She's changing animal forms, life forms, plant forms, and so on, just by light and sound radiation. That is resonance. We want resonance. You can start there.
Thank you very much.
Very interesting. And just on that note, Professor Roy, I mean, in terms of things coming into contact, like if you were to take a glass of water and set it on a picture of something, would that be a epitaxy in that way, that it would?
Well, yeah, and see, those are so weird that people used to think this is all a bunch of rubbish, right?
Right.
And it's getting a little less weird now. In other words, you can say, well, maybe those things are emitting. And especially in that kind of work, you remember that they used to say that silver photographs are much more powerful than digital and all that kind of stuff. And most of the people have said, and there's a damn good reason for that. The silver radiation, which is in Brooks's work, by the way. If anybody is interested, they really must read. You just go to the web and you can find all her work. They're largely in patents. There are about 50 patents. Very long, detailed patents. But the silver radiation can substitute for silver atoms. She's shown that. So imagine a photograph with dark and light silver. Maybe there can be something to it like that. So those are all plausible things. I mean, remember, plausibility is what is important to establish. You're never, without about $1 billion or $2 worth of research, going to be able to establish the kinds of questions that are being asked,
right?
In a kind of a definitive manner. But nothing definitive about pharmaceuticals anyway. So I think that what we should aim for is plausibility to make homeopathy more acceptable by the customer. It is all expectation. I mean, if you have an expectation, it obviously participates in the healing. And it should not be destroyed by bad science.
Well said. Well said. Is there another question in line? I don't want to monopolize here. The operator, do you have anyone else in queue with a question? It'll take a minute for her to beep back on.
Okay.
Is the operator there? Okay. Well, I am going to go ahead and ask a question then. Wait.
Ask your own question.
Let me just find where I wrote the question.
I'm sorry. This is the operator.
Yeah.
There's no questions pending.
Okay. So let me ask the question I had. So just in terms of looking at water in general, Professor Roy, so then things that we do to water, you know, putting it in the microwave or storing it in plastic bottles or all this reverse osmosis, I mean, we're changing water in ways that we probably don't realize.
We absolutely are. Actually, we are working very hard on the microwave stuff, and we are doing what that man did with radio frequencies. Microwaves are 1,000 times more powerful than radio frequencies, 1,000 times less powerful than your light bulb. So, but it can do the same kind of stuff. Yes, all those radiations can definitely change water. That's now established, and nothing more to say. And we'll be presenting that paper in November 27 in Boston. And so I think that is the kind of question which was regarded as outrageous before. Now that's over. It's over. Right. So I think we must know where we are in the progression towards some kind of conclusion. This is the first step, not a baby step anymore. It's a pretty big step to say that, yes, all kinds of radiation change the structure of water. Finished. It's over. They change it dramatically. Both microwaves, radio waves even, magnetic fields. So I think now the shoes on the other foot, people have to prove that this is not doing any damage and not hurting and so on, and one can claim. Now, whether the cell phones do this is a big thing. Cell phones are the same as microwaves.
Right.
Do microwaves change? Well, there's no doubt about it. It can change. It's a matter of how much, or what does it do, but no more can it be said that this is nonsense, you can't change the structure of water. And that's where homeopathy can build on. It can say, all the practitioners can say, now that it is firmly established that radiation, even in the gigahertz range, the microwave range, can change the structure of water, and even radio waves can change it, it is no longer sayable that water can't be changed. So
now the research is to what does it mean for it to change? How much does it change, and what's the effect of that change?
Well, this man's one thing is that you can not only change it a little bit, you can destroy it. You can break it up into hydrogen and oxygen. That is so fantastic. So, I think that the homeopathic community should be waving that with a big banner, say, why are they blaming us? Because here, why are they spurning us when a little radio wave can break up water molecules?
Professor Roy, I just had a thought, like the Petri dish idea with the colloidal silver. Could we possibly take, let's say, an infected someone who has, let's say belladonna-like symptoms, which is just a high infection, and take their blood and put a homeopathic dosage of belladonna in that Petri dish and see what happens? That's a very simple and inexpensive experiment, right?
I have always assumed that's been done 100 times, and you can look at the shape of the blood cells. In that water movie, if you've seen
I don't think it's been done. Has anybody heard of anything like this?
No, I don't think anyone's doing research at that level, not that I know of.
But we could take a simple infection with someone that we've known does well on this particular remedy and just see if there's any change in the blood.
I'm astounded that it hasn't been done, but yes, you're absolutely right.
And that's an inexpensive experiment.
That is very inexpensive.
I think we need to do a few of these. Okay.
Right. I think, Jenny, what you need is a convening of, in the light of this new work, which is emerging from Kansas and Erie, Pennsylvania, from these Penn State guys, Arizona State guys, how should we now proceed? And I think this looking around, waiting for NIH takes 2 years, but I think the companies have got to get off their duff and support some of these preliminaries, these are not expensive. This is not a clinical trial with 200 subjects.
Right.
This is a cheapy bit of research which they ought to get on with quickly.
So, Professor Roy, we could actually do it maybe in two ways. We could do the Petri dish idea. Let's say we just take our patient's blood right at the intake and put the remedy we want in there and then test the blood afterwards, after it's been exposed to the homeopathic remedy, as well as seeing how has this remedy done for that patient over, 6 months' time. We could do, which would be soft data in terms of, more testimonial, but we could have actually pretty exact data if we just then re-examine the blood following a homeopathic remedy.
Well, to me, that's astounding it hasn't been done, if it hasn't been done.
I don't think it's been done. It sounds very simple.
Yeah, I agree 100%. I hope you'll do it soon.
Okay. I think you really inspired something. Thank you very much.
Okay.
Are there any final questions? And then we'll let Professor Roy get on with his Saturday.
Okay, we do have...
Okay, go ahead.
We do have 2 questions pending.
Great.
Next one is Jean Laveau. Jean, please go ahead.
Hi, this is Jean. Thank you, Dr. Roy. I've been enjoying this tremendously, although I tried to get on with questions and couldn't. I'm wondering first whether you're familiar with Korzybski's work in 1933 in which he did sol gel experiments.
No, I don't know that. If you can send it to me, I'd be grateful. What did he do?
He wrote a book called Science and Sanity, in which he debunked linguistic approaches to reality and said that the basic assumptions hidden within language prevented people from understanding what was going on. And he introduced sol gel to me, at any rate. The work is Science and Sanity, 1933, by A.J. Korzybski.
Korzybski or Korzybski?
Korzybski, Korzybski.
Okay, Korzybski. I know him now, yeah.
Okay. The next question is the geometry, the structure that you refer to. The octahedra, dodecahedra, and tetrahedra I'm very familiar with because Dr. Sollett, with whom I was affiliated for 40 years, looked at structure of everything. And the basic structures that he had included these primary ones below the Platonic solids.
Platonic solids.
So I wanted to mention that in case more people wanted to know about these structures. I have a lot of data on that.
Yeah, no, I think that, and they're combined in complex crystalline matter. Those are interpenetrating Platonic solids.
Correct.
So, I'm glad I think those structures are universal and they're important in all crystalline matter. I mean, 99% of all solids are made up of those 3 or 4.
Well, his work goes underneath the Platonic solids to come up with a hierarchy of polyhedra. Again, if you want to be in touch with me about that, I'm glad to send you information.
Yeah, okay, thank you.
Great,
thank you.
Is there another question, operator?
Yes. Next one is Laurie Grossman. Laurie, please go ahead.
Hi. Thank you, Professor Roy. This was a great presentation. I've been pressing the dials on my telephone like crazy. The research that you said you're surprised that hasn't been done, Benavite did studies like this in the med school in Italy, I think it was Verona, where he tested the response to homeopathic dose substances, and he saw the effect of them on mast cells and on different cells in the human blood.
I know nothing about that stuff, so I would have thought, as I was saying, that has been done.
He did. I know his work was later, of course, criticized, but he explains a lot of that in the first few chapters of his book. I think it's called The Emerging Science of Homeopathy or something like that, but I do know that he refers to that in the beginning chapters of the book.
Mm-hmm. Well, I think that the other homeopaths that are listening in will be helped by that, and they can look it up.
Mm-hmm.
It is the Emerging Science of Homeopathy.
You know what, Jenny? I'll get you the correct name. I'm
Great.
not in my office. I'm hiding literally behind a synagogue. It's the Jewish holiday, so I don't have my books in front of me, but I can get them for you, and then you could disperse it to whoever's interested.
That might make it more effective. You're so close to a synagogue.
Yeah, right. I'm sitting here in the lap of God.
Actually, that turns out to be the title, The Emerging Science of Homeopathy, Complexity, Biodynamics.
Like yeah. That's it.
By Paolo Bellavite.
Right. That's it.
Good memory.
And it's definitely in the beginning chapters of the book. Because what he does in the later chapters of the book is he hypothesizes as to the mechanism behind it, which is actually brilliant work, which, of course, was also criticized, but...
Oh, we'll have to put that on our reading list for everybody.
Okay.
Are there any other questions, operator?
Yeah, I think what Dr. Kyle Peck said here is important. That group, Senorini and Bellavita, they will certainly read our work and adopt it into it, because this fortifies their arguments.
Right.
This is much more universal science related to homeopathy.
In fact, I would suggest that someone in your group bring that to their attention, because they certainly want to know it. But it's remarkable how discoveries in one field remain unknown to the other fields. And so you guys could play an important role in pointing them. Share Dr. Roy's PowerPoint with this author, and there'll be a new chapter in his book.
Great suggestion. Yes, we're learning to create more community here as homeopaths, which has not been.
I think what Dr. Peck pointed out, networking is extremely important, and here, small community, we can network. Yeah.
Great. Any other questions, operator?
Currently, there are no questions pending.
Okay. Melissa, did you have any final comments to make, and then we can...
No, I think we're fine. It's just been such a great resource, and talk about sharing of information from one field to the other that would be quite instrumental to how we could actually start to talk about homeopathy in these modern times in a way that really would be effective and put us on the map a little bit more. So I really appreciate the talk and the information and the sharing. It's been, I think, very invaluable. So thank you, Professor Roy.
Thank you.
Yes, thank you so much, Professor Roy. And he is going to forward us the video on the water and fire experiment that I will send out to everyone. And again, thank you so much for taking the time to speak with us this afternoon and sharing all of your invaluable work.
I'd also look at that Russian movie on water, which Catherine can send you. It's a huge file, but I don't think you can send it by email.
We have a server. We can have people.
But she can handle that. Okay.
Great.
Thank you.
Okay, thank you very, very much, and thanks, everyone, for tuning in.